Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So we are discussing about solid mechanics and material subject. So in this subject, in previous session already we have started this thin cylinders topic. So in this introduction about thin cylinders and how to calculate the stresses, what are the stresses induced inside the cylinder. So we have derived and analyzed in previous session. So in this today's session, so I want to discuss about some more topics related to this thin cylinders. So analyze the outcome of this topic is analyze the stresses developed and deformation of thin and thick cylinders due to internal pressure. So already we have analyzed. So after completion of this topic, the student be able to analyze the stress developed inside the cylinder due to internal pressure. So once again we will see the introduction to thin cylinders. So this unit presents the analysis of thin and thick cylindrical cells subjected to fluid pressure. So we are discussing about thin cylinders. So how to calculate various stresses induced whenever these thin cylinders are subjected to fluid pressure. So examples for the thin cylinders are steam boilers, reservoirs, reactors, nuclear containers, container tanks, working chambers of engines, etc. are the common examples. So in this unit, the stresses and strains induced in the walls of the cylinder will be found out based on the geometry of the shell and equilibrium of the forces involved. We shall begin by defining a thin cylinder, identifying the assumptions made in the analysis. So once again we will see what are the assumptions made in this analysis. After finding the stresses in the material of the cylinder, strains will be calculated. So these strain calculation part also we have completed. Stresses in wire wound pipes will be considered. We shall then see the limitations for treating a shell to be thin and look for the differences in the behavior of a thick cell as against a thin cell. So the following assumptions are made in order to derive the expressions for the stresses and strains in thin cylinders. So one is the diameter of the cylinder is more than 20 times the thickness of the shell. The stresses are uniformly distributed through the thickness of the wall. So these are the assumptions made. One is the cylinder, the diameter of the cylinder is more than 20 times of the thickness of the shell. The shell thickness greater than the cylinder diameter is 20 times of the shell thickness, 20 times of T. So then only it is said to be thin cylinder. The stresses are uniformly distributed through the thickness of the wall. So another assumption, the ends of the cylindrical shell are not supported from sides. So the weight of the cylinder and that of the fluid contained inside are not taken into account. So the atmospheric pressure is taken as the reference pressure. The cylindrical vessel with hemispherical heads. See, now we will see whenever the cylindrical vessel with hemispherical heads. So let us consider the vessel with hemispherical heads. I will show you the diagram. The wall thickness of the cylindrical and hemispherical portion is different. So whenever consider the vessel with hemispherical type shape, the thickness of the cylinder and the hemispherical portion is different, not same throughout the cylinder. While the internal diameter of both the portions is assumed to be equal, but in assumptions, so we will take the internal. We will consider the internal diameter of both the portions is assumed to be equal. Let the cylindrical vessel be subject to an internal pressure P. See in this diagram shown the hemispherical shell. So the thickness of the cylindrical hands T2 and the wall thickness is T1 and internal diameter, and this is internal pressure. So whenever the cylinder subjected to fluid pressure inside, so the pressure will act on wall thickness in two ends and then side walls. For the cylindrical portion, first you will take the cylindrical portion. Already we have derived the circumferential stress. So what is the circumferential stress or wove stress? So the cylindrical portion represent with C. So that the sigma HC, the PD by 2T1. So already we have seen in this, shown in this diagram, the thickness of the wall, cylindrical portion T1, and P is the internal pressure and the diameter of the shell. So the longitudinal stress, sigma L C, the PD by 4T1. The woof are circumferential strain. So already we have derived in the previous session. So one is longitudinal stress, sigma L is equal to PD by 41, and sigma H is equal to PD by 2T1. So the hoop or circumferential strain, that is, finally we will get sigma 2 is PD by 41E multiplied with 2 minus 4. So this is Poisson's ratio, and E is Young's modulus. See in this diagram the cross section of hemispherical shell shown. So here the T2 is thickness of the hemispherical shell wall, and the wove stress is acting on the cylindrical walls. This cross section shown here, the diameter, the internal pressure. See, whenever you are considering a small elemental portion of this hemispherical ends, so you can see in this diagram how the circumferential stress acting on these hemispherical ends. So for the hemispherical ends, because of the symmetry of the sphere, so here the symmetry of this sphere, the stresses set off owing to internal pressure will be two mutually perpendicular woods or circumferential stresses of equal values. So two perpendicular woods. See here shown this sigma H. So the perpendicular woods are circumferential stresses of equal values. Again, the radial stresses are neglected in comparison to the wove stresses, as with the cylinder having thickness to diameter less than 1:20. Again, The radial stress are neglected here when compared to the hoof stress. So why? Because the thickness of the diameter is less than the, so this having thickness to the diameter, T by D ratio is 1 by 20. So consider the equilibrium of the half sphere. Force on half sphere going to internal pressure is equal to pressure into projected area. So the pressure into projected area is, the pressure is P, the projected area is pi by 4 to T square. So this is, you will get the force on half sphere going to internal pressure. But resisting force, that is whenever internal pressure acting inside the fluid pressure, the resisting force is equal to circumferential stress multiplied with area. So that is pi d into T2. So the resisting force is this force on half sphere owing to internal pressure. So that is P into pi by 4 d square is equal to sigma h pi d into T2. So the per sphere, sigma h is equal to Pd by 4T2. Similarly, the Wolf strength 1 by E into sigma h minus mu into sigma h. So here take common outside, take outside this sigma h by E and 1 minus. So that is equal to, so sigma h already we know the Pd by 42 E into 1 minus mu. So after simplification, you will get strain, Wolf strain, that is epsilon 2 Pd by 42 into E into 1 minus mu. See here, shown here hemispherical hands. So dotted line shown here. So in figure 3, the shown the by way of dotted lines, the tendency for the cylindrical portion and the spherical ends to expand by a different amount under the action of internal pressure. So, owing to difference in stresses, the two portions, that is cylindrical and spherical ends, expand by a different amount. So, this cylindrical portion and these walls will expand with a different amount. So, shown here with the dotted lines, the expandation. So, this is after expandation, that is delta L, and delta D, how much diameter increase, and diameter. So that there is a difference in stress. The two portions, that is cylindrical and spherical ends, expand by a different amount. The cylindrical and then spherical ends. So this incompatibility of deformations causes a local bending and shearing stresses in the neighborhood of the joint. Since there must be physical continuity between the ends and the cylindrical portion. For this reason, properly curved ends must be used for pressure vessels. This incompatibility of deformations causes a local bending and shearing stresses. So thus equating the two strains in order that there shall be no distortion of the junction, that is PD by 41E into 2 minus mu. So that is equal to PD by 42E into 1 minus mu. And T2 by T1. So equate these two forces, stresses, and then you will get T2 by T1 is equal to 1 minus mu by 2 minus mu. Here general the steel work, the mu is 0.3. Therefore, the thickness ratio becomes T2 by T1 is equal to 0.7 by 1.7, or the T1 is equal to 2.4 times of T2. Clear? So that the thickness of the cylinder walls must be approximately 2.4 times that of the hemispherical spheroid ends for no distortion of the junction to occur. So, the thickness of the cylinder walls must be approximately 2.4 times that of the hemispheroid ends. So, that is, here see, T1 is equal to 2.4 times of T2 in this diagram. So, T2 and T1. The T2 is the hemispherical end 2.4 times of the T1. T1 is equal to 2.4 times of the T2. So now the summary of the results up to now what we have calculated. So let us summarize the derived results. The stresses set up in the walls of the thin cylinder owing to an internal pressure P. One is circumferential stress or wove stress SH or sigma H PD by 2T. The longitudinal or axial stress sigma L, that is equal to PD by 4T. So where D is the internal diameter and T is the wall thickness of the cylinder. So then the longitudinal strain epsilon L is equal to E into sigma L minus mu into sigma H. The wove strain 1 by E into sigma H minus mu into sigma L. The change of internal volume of cylinder under pressure. So that is PD by 40E into pi minus 4 mu into P. So here the change in internal volume of cylinder under pressure. So from thin sphere circumferential wove stress is PD by 2T. Already we have seen in a previous equation, PD by 2T for circumferential or wove stress, and sigma L is longitudinal stress. Now, what is the change in volume of thin cylindrical shell due to an internal pressure? So there is always an increase in the length and diameter of the thin cylindrical shell due to an internal pressure. The shell length will be increased. A little consideration will show that increase in the length and the diameter of the shell will also increase its volume. So whenever the length increase, the diameter also will be increased. And the diameter and the length increase, they increase its volume. So now consider a thin cylindrical shell subject to an internal pressure. So now take cylindrical shell subject to an internal pressure, we will calculate change in volume. Let the L is the original length, small d is the original diameter, and delta L is the change in length due to pressure. And delta d the change in diameter due to pressure. So already explained in a previous slide. Volumetric strain is defined as change in volume divided by original volume. The volumetric strain is how much change in volume to the what is the original volume. It gives volumetric strain. So you can represent with epsilon b is equal to delta v by b. So now the change in volume is final volume minus original volume. So the original volume is V, the area of cylindrical shell into length. The area of the cylindrical shell is pi by 4 d square into length is L. So the final volume, final area of cross section into final length. So initially the area of cylindrical shell already we know pi by 4 d square into length, it gives original volume. So the final volume, final area of the cross section after changes, dimensions or changes in the shell. So diameter increase and length also increase. So the final area of cross section is pi by 4 into d plus delta d. The previously the only diameter, but now diameter is changes to delta d, d plus delta d. So increase diameter and length also increase. So substituting this area of cross section and the final length. So here neglect the smaller quantities. The final volume is pi by 4 into d square L. Expand this equation 2d into L into delta d plus delta into d square. So we will get the change in volume finally pi by 4 into d square L, 2d into L into delta d plus delta d into d square minus the original volume. The final volume and original volume. So we will get change in volume pi by 4 into 2d into L into delta d plus delta L into d square. So now volumetric strain, the change in volume to the original volume. So much the change in volume delta V is pi by 4 into 2d into L into delta d plus delta L into d square divided by pi by 4 into d square dl. So we will get 2 into delta d by d plus delta L by L. So we can represent with 2 epsilon c plus sigma L. So circumferentially diameter and L is longitude. So delta V is V into, so delta V by V is equal to 2 epsilon C plus epsilon L. So delta V, V multiply with epsilon C plus epsilon L. So where epsilon C is circumferential strain and epsilon L is longitudinal strain. So these are the change in volume of thin cylinder shell due to an internal pressure. So up to now we have calculated all required formulas. So these are the references I have taken for this PPT. One is Ramamurthy, Strength of Materials. Title of the book is Strength of Material. And R.K. Bansal, the textbook of Strength of Materials. And another reference is R.S. Kurmi and Gupta. The title of the book is Strength of Materials. So, and also I have taken the NPTEL course material. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.